Hi, I promised that I would work out the last Go Formative question we asked today because it was really complicated and kind of rushed at the end. So hopefully I'll do it a little bit more logically here than I was able to help with in class. So here was the question, and it was a combustion analysis question. And our goal is to find out the empirical formula for this compound that they said contains carbon, hydrogen, and oxygen. So you know it's a combustion analysis when they give you the amount of carbon dioxide and water produced. Okay, and hopefully you know that the word burn means combusted, right? All right, so I also wrote down a series of steps that you can follow when doing combustion analysis in case that helps anybody. So the first thing that you want to do is find the moles of carbon in the compound by starting with the given mass of carbon dioxide. And I'll show you how to do that. But so that's, you take the first given and you're going to convert that through stoichiometry to the moles of carbon. Then in a very similar step, you're going to also find the moles of hydrogen atoms starting with the given mass of water, okay, which in this case is 2.54. Once you have the moles of carbon and hydrogen, if those are the only elements in the problem, you're simply going to go through the steps of how you get from moles to an empirical formula, the same procedure we used in getting empirical formula from percent composition, and that is you divide all of the mole values by the smallest mole value, and you hope that it gives you whole integers. If you get whole numbers or numbers that are close enough to round to a whole number, you now have your empirical formula. If not, you may have to do the multiplication by 2, 3, or 4 to get whole numbers. So what makes this particular problem extra complicated is the fact that in addition to having carbon and hydrogen, it has oxygen. So steps 4 and 5 that I have on the bottom here are only when oxygen is part of the original compound that's being combusted. In that case, you will hold off on doing 3 until you have oxygen moles determined, right? So you go straight from 2 to 4. So after you find the moles of carbon and the moles of hydrogen, if there's oxygen there, you will take the moles that you found one step further and calculate the mass of carbon and hydrogen from these mole values that you just found. The reason you have to go to mass of just the elements, carbon and hydrogen, is so that you can then use the conservation of mass to find the mass of oxygen in the compound. So the bottom line here, conservation of mass, I think, let's see, this problem was, I believe, 4.26. Why is that not working? Interesting. There. That was 4.26 milligrams, the total compound. And since that compound consists of carbon, hydrogen, and oxygen, the grams or mass we have of each one of these needs to add up, right, to equal the mass of the compound, conservation mass. So by rearranging this equation to solve for the mass of oxygen, right, move the mass of carbon and hydrogen, subtract them from the mass of the original compound, you can find the mass of oxygen. Here's the information that was given to us in the problem. We have the mass of the original compound, and we have the mass of the two products. Now, we can't use conservation of mass in the way that we're used to because one of the reactants, that's molecular oxygen from the air, we don't know how much of that was combined. So we can't, in this case, say that or use the fact that mass of all the reactants will equal mass of all the products, right? Because there's no way for us to know how much oxygen. But we can, in fact, say that the mass of this unknown compound that we're combusting will equal the mass of its individual elements. Alrighty, so that's what we're going to aim to do. All right, so step one was to start with the mass of CO2. Now, notice these are in milligrams. You don't have to switch them out of milligrams. It really doesn't matter what unit all of the masses are in, as long as they're all in the same mass, because you're going to be taking a ratio of the moles to moles. So the ratios are not going to change, whether you have millimoles, moles, megamoles, whatever. So you don't really have to spend your time converting out of milligrams. Just make sure they're all in the same units. All right, so I'm going to keep it in milligrams. And the first thing you want to do is, that is CO2, is you want to convert to moles of CO2. So the molar mass of CO2 is 44.01 grams per mole. And I don't have to convert molar mass to milligrams either, and I'll show you why. This gives a convenient little unit called millimoles. So 0.1411 millimoles of CO2. All right, and then we really want to get to moles of carbon, the element carbon itself. So now I need to do a mole conversion from moles of CO2 to moles of carbon. So I need a mole ratio. Anytime you go from one substance to another, you need a mole ratio. And so for every one CO2 molecule, I have one carbon. There's only one carbon in CO2. So that means I have the same number of moles of carbon. So I have now found the moles of carbon, and I'm going to do a really similar calculation starting with the given grams of water. So 2.54 milligrams of water. Find the moles of water by dividing by molar mass. And I will have the millimoles of water as soon as I punch that in my calculator. 2.54 divided by 18.02. And so that gives me 0.14095 moles of H2O. I need a mole ratio now so that I can go from moles of H2O to moles of hydrogen. So let me go ahead and see if I can squeeze that in here. All right, so again, I'm trying to go from moles of H2O to moles of the hydrogen atom. So how many hydrogen atoms are there in one H2O? Okay, for every one H2O, there are two hydrogens. So that mole ratio is 2 to 1. So that is going to tell me then that the total moles of hydrogen I have are 0.2819. Right. So I have moles of carbon and hydrogen, and if oxygen was not in this compound, you'd be almost done. You just have to divide by the smallest mole value, which in this case is carbon, and then just get the mole amounts of each of them, and that's your empirical formula. But since we have oxygen, of course, life is not that easy, and so we need to go on and do the later steps that I listed on the previous page to figure out oxygen. So to find oxygen, I have to use conservation of mass. So I need to take the moles of carbon and hydrogen that I just found on the previous page and convert them to mass of only carbon and mass of only hydrogen. So to get from moles to grams, I multiply, instead of dividing, I multiply the molar mass of that element And let's see what I get there, 0.1411 times 12.01. So that's 1.695 grams of carbon in that compound that was combusted. So this is telling us how much carbon is literally in this 2.46 gram sample. And let's see, hydrogen, to find the grams of hydrogen, I'm going to multiply by its molar mass for hydrogen atom. It's 1.01. All right, so 0.2819 times 1.01 is 0.2847 grams of hydrogen. All right, now we can use conservation of mass. So the mass of the compound, which was combusted, that was given to us in the problem, and it has to. Whenever you have a compound that contains oxygen, they have to give it to you. 4.24 milligrams. And yeah, these are actually milligrams too. I forgot because I didn't change out of milligrams, so they're still in milligrams. All right, and then that has to equal the mass of carbon plus the mass of hydrogen plus the mass of oxygen. So the mass of carbon that I just calculated is 1.695. The mass of hydrogen is 0.2847. And then the mass of oxygen, I can rearrange this and solve for that. And by doing that, I then get that the mass of oxygen is 2.260 milligrams. All right, so now I have the quantity of oxygen, but to go back to the mole or to the empirical formula, I need moles of all of them. So I had already calculated the moles of carbon and hydrogen on the previous page. It turns out, right, I already have the moles of carbon and hydrogen. They were the first two calculations I did. And I only have grams or milligrams of the oxygen. So I need to get moles of the oxygen. So I'm going to do the same thing I did to find moles of carbon and hydrogen. I'm simply going to multiply the mass I have times the molar, or divide by the molar mass of oxygen, which is 16, if you round it correctly, exactly. Okay, and that will give me millimoles of oxygen. So 2.260 divided by 16. So the moles of oxygen, or millimoles of oxygen, are 0.14127. You may notice that I am carrying all sorts of extra digits to the right of the decimal. I carry extra digits to the end, so I don't round to the end. So there we go. Now I have moles of everything. As long as you have everything in the same units of some type of mole, whether it be mole, millimole, megamole, kilomole, whatever, you can now divide by the smallest value and hopefully get whole numbers. So let's see what happens. What is the smallest mole value? Okay, it looks like it's 0.1411. I mean, these are probably essentially going to be equivalent, right? So we're going to divide them all by 0.1411 and see what that gives us. So let's see. When we do oxygen divided by 0.1411, we get that is 1.00. That's oxygen. And when we divide it by itself, of course, we're going to get 1 millimole of carbon. And then it looks like for hydrogen, we're going to get 2.2819 divided by 0.1411. Yep, 2. So we now have our empirical formula. There is 1 carbon. Sorry about that. There is 2 hydrogen, R 2 hydrogen, and 1 oxygen. That's it. That's the empirical formula. Now in the next slide, I'll go ahead and tell you how you find the molecular formula. I threw that in as a part 2 just to see if anyone could figure that out, but I think your brains were probably ready to explode at that point. So next slide, I'll walk through that. Anytime you are asked to find the molecular formula, once you found the empirical formula, the problem must give you the molar mass of the molecular formula. So the problem said, part 2, said the molar mass of the molecular formula, the actual formula, is 180 grams per mole. So you can calculate the molar mass of the empirical formula now that you know it, right? So it's got 1 carbon, it has 2 hydrogen, and 1 oxygen. So the molar mass of that empirical formula is 30.03. Then you simply take the ratio of the molar masses. That tells you how much bigger, if at all, the molecular formula is compared to the empirical formula. So 180 divided by 30 is 6, which means the molecular formula is 6 times larger than the empirical formula. So all we do at this point, take the empirical formula, multiply it by 6, and what do you get? Well, all the elements just multiplying by 6. So now the real formula, the molecular formula, is C6H12O6. And that's it.